صباح الخير. Do you see the screen?
Yes, we see it.
Okay. I will try to complete the motor protection. It requires more than 2 lectures, but anyhow, today I'll try to. I have just a few less than the lecture time. I'll try to complete as I can, and if I have time, also I'll maybe present it at another. So in the previous lecture, I have presented the introduction, and I reached the how do we set the overcurrent, instantaneous overcurrent to detect short circuits. So we use the 50 elements and 50N elements, okay, and to provide a short circuit protection. And normally we set these relays higher than the maximum locked rotor test. Sorry, maximum lock rotor currents. And we can use one stage or 2 stages. So stage 1, when you bought, normally it should be time delayed stage 1 because it's very close. It's higher than the lock rotor by 20%. So the asymmetrical or DC decaying content in the starting current can make this element, if it is set at close to the lock rotor current, can make it pick up. And that's why we should delay it by a time of 10 cycles roughly. But the instantaneous one, which you call it high set number 2, because it is beyond the this asymmetrical current, so it can be set instantly with no time delay. And that's why we set at 1.7 to 2 times lock rotor currents. But this doesn't provide the if a fault happens here of the rotor is locked while starting, or it's running and then locked, so the current will not see. This is only protecting faults. So what would happen if the current is here? So the motor can withstand this during acceleration. It can withstand this time before it gets damaged. And that's why we need additional protection. Similarly, when during normal running time, and sometimes motor can be overloaded, so we are working in this region, and that's why we should provide additional protection. So what are those additional protection to detect other type of faults? And this is for the settings of what I have mentioned. And this is how we connect the ground overcurrent protection. And this is the core balance CT, if you can, the black one. And those are the conductors of the 3 conductors, but each of them is maybe for large current. We use more than 1 conductor. Maybe this is not necessary. So these all passing through the core of the core balance CT or zero sequence CT, or okay, we call it sometimes also flux summation CT. All this means same. So all the conductor pass through the core of the CT, and this goes to the we call this in this case 50 G or 51G in this case, if you do it in this case. Okay, but if I take the CT from each this and we sum them, okay, then this is 50G. We sum the current IAIB by using this. If I take this, say, the summation of the 3, like here, I measure the current of the sum of the 3. Whether it is by calculation or by connection, we call that 50G. 50G. And we have 50N. This is, sorry, the 50N. Second is the, differential. Differential, I have already covered this in the differential protection, but what I will add, this is what I have covered, okay, and how the connection, it is biased differential protection, but sometimes for some, like this is sometimes we can connect it in this way, if possible. And this is called the self-balancing differential protection, as compared to the phase uh, differential protection, or the conventional phase differential, what is this percentage or bias differential protection. This is what how we connect it. So one day to use this, what is the advantages of this? For this, first of all, differential protection is used for large motors, for detection of line to ground faults and phase faults. Uh, and it is very sensitive. It's not affected by the starting current or the, okay, it's like the instantaneous overcurrent relays. Um, like this one's, it is more sensitive as compared to this. This is only one CT. As you can see, the before we make the star point of the motor, we pass it through the CT. This is one CT here, one CT here, and one CT here. So we take the two. Now this is possible if the conductor size are not big enough to pass it through the CT core. If this conductor very large that you cannot pass it through the window of the CT, then this is not possible. We go for this one. And normally this, they call it the self-balancing CT connection. Normally, this is 50 to 5 ratios as a typical ratio we use, while these ones we should take them considering the full load current, these CTs, as I mentioned in the previous chapter. As I said, this is independent. This is a connections very sensitive, independent of the load current or starting current. But its limitation, two limitations. It's the window size of the CT through which you can pass two conductors of the end of the two motor terminals. Uh, uh, and the second disadvantage that if the breaker is here, it does not include the breaker and the wiring connections. While here it includes, let's say, the cable that could connect between the breaker and the motor, okay, is included. If a fault's here, it's included. A fault in the breaker is included, while here it's not included. So the zone of protection is smaller as compared to here. There are some also situations where يعني the differential is very critical and important for such situation where for example, when the starting current becomes very close to the fault current. So sometimes you cannot set those elements, the instantaneous. So the solution here to go for the differential protection. And also we cannot apply differential in general if the terminals of the motor, these are internally connected. You cannot access the ends. So in that situation also you cannot, there are some motors that the end is internally already connected as a star, or so you cannot, in this case, apply differential. Normally for larger motors, these are not an issue. Another protections, so what I covered now, short circuit protections. Now, other protections is under voltage. protection, which I have not covered in the previous chapters. We use under voltage protection uh, when the voltage reduce for long duration lower than the rated voltage. And this is to, when this happens, when the voltage drops below rated voltage, the current will increase for motor, because imagine the load is same and a voltage drop, mechanical load is same. If the voltage drop, the current drawn will be higher, so that you get the same mechanical power. Okay, so current will increase, and that situations will cause overheating. And similarly, when the or at some situation of under voltage, some level of under voltage, the motor can stall or even fail to start if you want to start it. So that's why. Uh, Now, if you don't have under voltage, what would happen? You know, there will be an increase in current, and there is an overload. Protection will act, but you don't want to. If you can detect this situation before it happens, you don't want to wait for the overload time, because you know it's the current increase due to the voltage level. Okay, so you can act faster. Uh, So also this is provided if you want to prevent, suppose there is a dip in voltage, okay, and drop in voltage, let's say to 40%. And because of this, some, let's say, contactors will switch off motors. And or suppose you really acted and tripped the motor. You don't want to, or once the supplies comes in, you don't want the motors to get started again, or all motor to be simultaneously started. And that situation will cause high inrush currents for all the motors. And another voltage dip will occur also due to high current draws. So when you set this one, this under voltage protection, you should consider the following: that normally by motor standards, motors are able to continuously operate at 90% of the rated voltage. يعني if the voltage within 90% of rated voltage, it is fine. يعني you shouldn't take any action, because the motors are designed uh, to operate up to 90% normally, continuously, with no issues. When the voltage drop below 90%, this is, we call it an under voltage situation. So how do you set it? We can set for alarm, uh, and for alarm when a voltage below 90%, we can say 3 seconds alarm. And if the voltage even, let's say, less than 90%, sometimes I've seen standard they use 85% of the rated voltage. Sometimes they go even 70%. If the voltage drop to 70% with some time delay, okay, then you take an action. uh, but mostly under voltage is time delayed, it's not instantaneous action. Okay. uh, Now, for when you set the time delay, you have to take into consideration also other, that you don't want to take, يعني, sometimes when a fault in the say, system, suppose the fault in the bus here, where many motors are connected, or in the line before, in the main feeder, I don't know if, okay, then you don't want, the voltage will dip, and you don't want to take action because fault is not in the motor. Or and also similarly, when you start a motor, voltage also drops, and you don't want to act during the start, the voltage drop due to the starting current. Okay. uh, so you have also that time delay has to take into consideration also the starting current, or the voltage drop due to starting current. You should wait more than the starting current. Okay. or sometimes we have fast bus transfer. يعني sometimes we transfer it from one bus if the bus need to be maintained or have an issue with the bus fault, you can transfer the motor to another bus. So if you want to transfer the from motor from one bus to another, bus will be dead before it gets transferred, and now we'll have a dip in voltage. And some motors you can transfer them as far as the voltage is not below يعني voltage will not dip directly in the motor magnetism, so it will take time. So you have transferred before the motor uh, يعني speed drops below, let's say, certain level. So this is our calculated design dependent. For over voltage, same. Majority of motor are designed by standard to continuously operate at maximum of 110, 10% more than the rated voltage. So you don't want to act if this happens. Uh, um, so why do we need to provide over voltage? Basically because uh, over voltage cause also over current. Okay, and not only is provide over voltage will damage normally the insulation. Okay, which is designed at certain voltage, and uh, and that will cause the life of the insulation will degrade. Now, when we set this one, as I mentioned, we make sure that we don't trip when it is within 10% of the voltage. Uh, Mostly this elements is for alarm. We don't use for tripping actions. If you want to use the alarm, you can set it at also 110. Uh, and for tripping, you can set it at 115 with a time delay. Uh, as per IEEE standard C37, they typically this type of protection is typically disabled, and they say because steady state over voltage is not generally an issue. Okay, it's not normally occurs a lot or an issue for motors in general. So mostly when you go to the protection of a motor, you will not see an over voltage protection there, or it could be just for alarm. This is very important protection, the current imbalance protection, uh, the 46. And current imbalance, you will see it in many like medium size and large size motors. Even small size low voltage motors, you can find it such protection of, let's say, motor compressors or motors in central ACs, and you'll see current imbalance or motors. So what does this do? First, why do we want to protect for imbalance? Because the current imbalance is can be first of all can be caused due to several reasons. One of them is the imbalance voltage. The voltage supplied to the motor are not equal. Okay, um, so a 3.5, for example, imbalance in the voltages can produce 25 increase percent increase in temperature due to imbalance voltages produce imbalance current, which is negative sequence currents, and that negative sequence current heats the motor rotor conductors and increase that by 25%. Um, So a 5%, for example, of negative sequence voltages due to the imbalance can also produce imbalance current of 30%. 30%. See, 5% in voltage. Ambulance measured as a negative sequence voltage produce 30% negative current. So almost 6 times. So sensing a current than a voltage is more sensitive because just 5% in voltage, negative voltage change can produce 30% more in current. So sensing a current is more. That's why current-based ambulance detection is more sensitive than voltage-based ambulance detection. Um, so what causes also this imbalance currents, first of all, and the voltages and the supply has nothing to do with the motor. Single phasing, if you lost one phase, maybe a fuse blown or breaker, one of the breaker could not close one of the phases. This cause also imbalance. Imbalance loading in the loads. If you put single phase loading different, and then that cause also voltage imbalance or current imbalance. Single phase faults. If you have faults in a single phase in the supply side, also that cause, or in the motor that cause also uh, imbalance current. But this single phase currents faults is already detected by the air fault protection that I have presented. So this is not an issue for us. This is what will not be detected by the overcurrent protection. Uh, so how do we this we normally measure. There are different ways. The old way they measure the difference in currents between magnitude in currents. If the, let's say if you lost one phase will be zero, the other will have high current, let's say increase by 70% increase in the other phases, and this is an indication of loss of phase. Okay, and you can take action. But the more sensitive way than using the magnitude of the current, phase current, is to use the negative sequence current measurements. Uh, so negative sequence current causes normally because of unbalance in voltages, due whether it is to endurance voltages or due to loss of phase, it will create a negative sequence current, and this negative sequence current will be of a double frequency, and that will cause skin effects because of higher frequency, and the rotor also resistance will increase as a result, and due to higher current and higher resistance of the rotor, the combined effect will increase the rotor overheating. Um, so what do we have to consider when we set the this element is to use as per IEEE recommendation. We use this normally for 750 kilowatt or 1000 and above motors. Um, it should be considered for certain critical. If it's even less than 1000, but this motor is critical for the like chillers of motor of central ACs. Okay, even if it is less than 1000 HP, still we use this types of protection, the current unbalanced protection. Uh, this So the ambulance, you shouldn't make it instantaneous because if there is an external fault in the motors, in the bus or whatever, you don't want to uh, act this because you want to have a coordination. So other overcurrent relays will take action, and you don't want to. So that's why these elements are always delayed. Uh, and also during inrush current, during starting current, the currents are asymmetric. If you add them, there will be also a current, unsymmetrical current, or a zero sequence current, or okay. So that's also you want to delay to avoid this situation. This is the general settings for this. The pickup at 15% of the uh, rated current. 15% is very sensitive, and because now we are talking about negative sequence current. If it becomes 15% of the positive sequence current or of the rated current, and delayed by 5 seconds for tripping, and for alarm, you can go for higher time and lower settings. Uh, Phase sequence protection. This is also can provide phase sequence. You can detect phase sequence also based on current, but normally voltage is used now. Now, when you want to see if the three phases coming to the motor are have the phase sequence, right phase sequence. You know, you covered in power systems, we have the supply can be a positive sequence or a negative sequence. If you reverse any two phases, the motor rotation will reverse because you change the sequence of phases. And some motors or some processes, we want to prevent motor turning in the other direction. And that's why before you supply the three phases to the motor, we would like to check if the sequence is right before I switch on the motor. And this is provided by this type protection. So based on the voltage, this is you are measuring now the negative sequence voltage. So I need have the VT. From VT, three-phase voltages I convert to sequence, and from the sequence, negative sequence voltage, I check is the negative sequence high. Then that's indication of a phase reversal. Okay. What's the detection principle? During normal operating condition, the supply voltage is a positive sequence. So it is 1 per unit, let's say, of positive sequence voltage. When you reverse any two phases, the supply also becomes 1 per unit, but negative sequence. Okay. And once negative sequence is detective, is very effective. This is to detect phase reversal. Now, the setting can be both, let's say, a 20% of negative. The voltage is 20%, the negative sequence voltage is 20% of the rated voltage, and 0.2 per unit of the rated voltage. That's indication of a reversal, and you take an action. So this is very effective even to detect loss of phase, or two phases loss, or reverse and phase sequence. This is the most important. You cannot find any motor without thermal overload protections. I can similarly, the phase sequence protection is also very important. You can find it in many, but if you have like a negative imbalance, this can also, some protection can be also detect. I can find the negative sequence voltages to detect also phase reversal. For thermal overload protections, it's provide protection from overheating of the stator and rotor windings, or if it is squirrel cage, also we want to prevent overheating in the rotor. So during, let's say, running, we have some situations of overload while the motor is running. Normally, overload condition is considered when the load is higher than the service factor times the full load current. Have you heard about service factor before?
No, doctor.
A service factor, if you go to any data sheet of a motor, even in the nameplate, you will see the service factor 1 or 1.15, which means if it is 1.15, means the designer of this motor is design the motor such it can be overloaded up to 15% extra to its full load if it is 1.15. So in this case, you don't want to trip the motor when it is still within the designer uh, limit of overload. So this is a permissible degree of overload. So if it is one, means your full load your full load current is your limit. So if the current is higher than full, it's considered an overload. But if the surface factor is 1.15, then anything higher than 50% of the rated current, then it's considered as overload conditions. The second is you want to overload happens during starting. If you start the motor while the voltage is not high enough, or it is there is jam on the starting, so to want to accelerate. So this is called a stalling, or motor starting, then voltage dip, and you don't have under voltage protection. So the motor kind of stall, and it will hold, it won't move, and this acts, it will draw the locked rotor current in this case. Okay, uh, so that will يعني this would subject the motor to extreme heating in the stator and rotor winding. The third, during a running ambulance situation, and it's not running an overload, it's an ambulance. As ambulance current causes, as I said, excessive heating, as I mentioned before. So even if we don't have a negative sequence ambulance protection, the 46, which detects the situation, even because of ambulance or loss of one phase will increase the the current. This in the other phases, that's why the overload will act. Okay, so that's why this is very important protection principle, which is widely in any motor will see this at least, thermal overload protection. And what do you want to do here? We want to match the overload relay characteristic close to the thermal and lock rotor curves that I have presented at the beginning here. The characteristic, this one, you want to bring it very close here so that you fully utilize the potential of the motor. You don't want to trip the motor if that is not as the overheating, it does not reach the limit. So how do we detect the how do we provide the thermal overall? We have an old relays, normally electromechanical relays, they use something called bimetal elements. Two metallic type, it is a piece of metal of two types. They expand if due to heating of current, and from the expansion it hits something and trip the circuit breakers. So this is called a bimetal type, uh, and due to the current passing, it will produce heat I square R that will bend the bimetal and trip the motor. The problem with this is it is uncertain. Ambient temperature can affect its operation. It does not, the characteristic of this bimetal does not exactly match the motor thermal limits. Okay, and generally those types of protection or relays are standardized by class 10, class 20, class 30. And what does class 10 means? In class 20, this classify based on time delay that you want to provide by this relay during overload at when the current at 600% of the full load, 6 times the full load current, which represent the starting current, because you don't want to trip during starting. So what is the maximum allowable time you want to wait before this thermal overload acts? So if you put class 10, it will wait 10 seconds at 6 times the full load. If you put 20, class 20, it will wait 20 seconds at this full load current, 30 seconds delay at this time. So this is one family of overload relay which is before widely used. And, still now, even if you want to model this in electronically, they model this this sort of characteristics or delays. The second method is used in especially large motors. We use RTD, resistance temperature detectors, which is directly, this is abbreviated at 49R or 49R. 49R for thermal for the rotors and S for the stator. So in the stator winding, there is a device that inserted in the winding, and sometimes we use to measure the shaft bearing temperature. It's directly measure the temperature. We don't use current to produce heat and heat change the bimetal and that trip the motor. No, this is directly measuring the temperature of the winding. So for three-phase motors, normally each winding will have two sensors, two temperature sensors. There's two RTDs. So we have a total of 6 sensors on the stator windings. For stator, if it is if the rotor is squirrel cage, you don't have it. You cannot have these sensors. Okay. Normally commonly used for motors more than 250 HP and above, and for critical motors to measure the hot spots in the motor. So this normally detectors will be influenced by the ambient temperature, uh, 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 the issues with this. Of course, this is needed because what you want is sometimes motor heat increases because of loss of the cooling, like the cooling pump failure, or the inlet air uh, for the ventilation is reduced, and that will increase the room temperature of where the motor is located. So that will be sensed by this. However, the problem of this types of protection is we can go to use it for alarms, but uh, for acting fast, this has a time delay response. Okay, especially at stall time, we don't want to wait a long time to wait for a temperature to increase, because you know it is stalling, and so this is the time delay. It has delayed. So instead of this, we use, or sometimes in addition to this, we use something called relays with thermal replica model. We model how the motor thermal limit as a function of current. Okay, so this is like modeling. Show something a model. I'll show you, inshallah, one slide that shows this. Now, what is the standard curve used in relays for instead of bimetal to model a bimetal action? Uh, this is how, this is the standard curve of from the current measurement. I can model the thermal overload characteristics. Like this is the IEEE standard or NEMA standard overload curves. So we have 15 curves, each specified, each provide different time element. As you can see, the pickup here at which this overload operates at almost 1.05%, 1.05. So when the current, let's say 6 times full load, this is the situation when you have a starting current, you don't want the overload conditions to occur. Like curve 1 will provide you 2.5 seconds. So for motors that the starting current is with less than 2.5, so it's more than 2.5 means this overload will trip. This is the tripping action by the overload. So if you take curve 2 provide 5-second delay. If you take, let's say, curve 15 to provide you 37 seconds delay. So as you can see, the characteristics like time inverse characteristic we covered in overcurrent. This is like the time multiplier. We call it the curve multiplier. And times 87.4 over I square minus 1. So if you want, as when you took 2, you double the time delay. So you take 1, you take the 2, so instead 2.5 it goes to 5. If you take 15, it will take 15 times 2.5 if you care 15. Now, so these are the current. This is what current is. This is the current, the current measured divided by the setting, the equivalent, the pickup setting. So the current input normally, we take some relays. They use the positive sequence current square plus the negative sequence current square times a constant factor under square root. This is the current here divided by the pickup setting. So this describes how long the motor can handle the overload current before it gets tripped before we reach the thermal limit of the motors. So which curve you choose, it depends on the this characteristics. You bring this the thermal overload close to this. Okay, you choose the curve that closely match this one and but below it. Okay. This is IEC standards. This is IEEE standard curves, and this is IEEE IEC standards curves. Same, but here we need to add. Sorry. So this what is this K factor? K factor represent the negative sequence resistance of the rotor to the positive sequence resistance. If this is not available, normally you can take 3. And there are also other ways to estimate these factors. It's like 175 divided by the look rotor current square. So why they use I equivalent rather than the current actual current? In order to take the negative sequence current due to imbalance into consideration, because negative sequence also will increase the heating in the rotor, okay? And you want to take that effect into consideration. Now, it is because the positive sequence, negative sequence has not same proportional effects, that's why I use this factor. And to take also the effects of the increase in resistance of the rotor winding due to the skin effects, due to the negative sequence current. This is another curve with standard curves for the overload from IEC standards. Now, how do we provide those now? The basic current protection, as I mentioned, the basic one, I need an overload protections plus an overcurrent, okay, for short circuit protections. Now, now I can combine the overload elements with 51 elements with the time overcurrent protection. Both of them will give me an overload protection for moderate overload when the overload here, and for when the overload excessive close to the locked rotor, and for also locked rotor protection, we the 51 elements provide this protection. The when they have a short circuit, the current is somewhere here, then the instantaneous element will provide this protections. So how do we set the normally overload setting? Normally overload settings, the 49 elements normally set at 1.05 or 105% times the safety factor times the full load current. Why take a safety factor? Because, you know, as I mentioned, we shouldn't trip the motor when the current is within the safety factor. So either this is 1 or 1.15. This is how we set the thermal overload for the pickup setting, and for the time setting, you choose the curve, okay? The curve that at, let's say, the starting current at this current, the curve here, this time provide a delay higher than يعني a delay higher than, if you want to use just an overcurrent, delay higher than the starting current, so somewhere here, okay? Or sorry, a delay higher than starting current and below, just below, يعني as you can see at starting current somewhere here, the overload curve is just below the limit, thermal limit. The overcurrent relay, the 51 limit relay, will provide the lock rotor protections, and it's set normally. So where's this course? How do you set this? Should normally below the also the thermal limits or lock rotor, and there is one point here we call the safe lock rotor time. This point, and this curve has to be below it. Okay, the safe stall time, they call it safe stall time or lock rotor, the time limits at lock rotor current. So this has to be below it. And the pickup setting is 115% of full load if it for safety factor 1, or 115, 1.15, 125% for a safety factor of 1.15. The instantaneous, already I mentioned this. How do we set the instantaneous element? So if you combine the three, this is the thermal overload limit of the motor, and this is given by the manufacturer. And this is the point where safe stall time, or the time delay that the motor can withstand before they get damaged when the current is equal to when the rotor is locked, it's not moving, and you apply rated voltage to the motor. This is the time before it get damaged, the motor winding get damaged. So this is the limit that you should not exceed, and this limit is achieved by combining the two. Uh, I can have an overload that is something like this. Okay, the problem, I cannot have an overload something exactly like this. So it might here. So what would happen here? I will lose the coordination here. When the current at lock rotor, the overload will not trip correctly. يعني you will exceed the thermal limit depending on just an overload during lock rotor. So here when you combine the two, effectively you are getting this due to the thermal overload protection, and for the overcurrent you will get this, and that's why you protect the motor from overload during light overload and during locked rotor condition. You can rely on one bimetal, one thermal element instead of using 51. Still using, you can use a bimetal element, sorry, thermal overload elements, but doesn't give you exact matching with the thermal limit curve of the motors. This is instantaneous, as I said. It's set at higher than asymmetrical force, so we can set it at 1.7 times the full load current. Others already explained before, and it can act instantaneously. The RTD bias, we can combine them for alarming, or we can combine it with with the the bias model with, as a bias, as an additional. There are also different settings. We can set it at 40 degree, um, when a temperature at 40 degree. This is the first point where I have no problem with thermal limit. This is called uh, uh, the the temperature. This is the thermal capacity used. TCU, thermal capacity used, means how much of the thermal limit that you have used so far. If it's 0, means we have not used. 100% means the motor is the thermal limits you already reached. So, and this temperature, based on temperature, you know what's my limit. Now, if the temperature is 40 degree, which is the normal temperature, ambient temperature, normally the ambient, the insulation ambient temperature is 40 degrees. So there is no heating effects. When the temperature, let's say at 130 degree, now you will reach 25% of the thermal limit. When the temperature reach, uh, let's say 155 degree, this is, we are talking about one of the classes. Class, I mentioned this class, we have class F, class H, class F insulation. Each of them has a temperature limit. So when for a class, for example, for the class, this is class F, for example, the maximum limit is 155 degrees. So when the temperature sensed by this RTD is 155 degree, means you reach 100% capacity, thermal capacity, and you have to take action. Now let's take an example. Do you have time, Shabab? Or do you want me to stop? Are you still there? Do you want me to stop here? Or you want me to continue, finish this example?
اللي يريحك لي سوري.
Okay. So let's see, let's put what you learn now into practice, okay? I'll show you one example. بس إذا أنتم يعني مو منتبه يعني saturated, يعني you will not benefit out of it. Okay, but you can maybe review. I'll see. I'll go over it. I'll see. طبعا لما نقول احنا thermal modeling, يعني thermal modeling is not يعني how they in a relay we model this, how the heat increase during running, for example, or heating, and how when you decrease the load, the thermal temperature will decrease, And if you stop the motor, the temperature will decrease till it reach the room temperature. So this is the heating effect has to be modeled, and the cooling effect has to be modeled. And this is done by derivations. Okay, uh, you model this as a function of current. Okay, and until you reach an equation that represent best the thermal protections as a function of current. So I didn't mention this because of time limitation. So each relay manufacturer can have a patent on how they model the thermal limit, okay, uh, using different parameters. So this is an example. I have a motor, and this switch on off by a contactor. This is 500 HP motor. It's not big enough, so it's less than 1000 HP, the first type. We can use, as I mentioned, for those less than 1000, we can use normally either fuse protected for short circuit, or I can use a breaker, uh, a breaker which has a magnetic element to provide short circuit protection for them. For the overload, normally provided by the thermal elements. So I'd say these are the basics, okay? Uh, Short circuit protection and thermal overload. Regardless of what I mentioned before, under voltage, over voltage, or phase loss protection is like the so this is how now we have, this is the breaker, the maximum rated current is 200 ampere. We want to set it, right? Set the current settings of this, uh, and okay. And I have here, this is the bus where I have different motor are fed from this bus. I'm showing only one motor. And here the main breaker has 6 ampere of maximum current. And this is also thermomagnetic. We'll say thermo, it has a bimetallic element. Magnetic, it has a coil that provides fast action. So this is like circuit breakers. This is also circuit breakers. Now, this circuit breaker is not like the circuit breaker for high voltage. Circuit breaker for high voltage doesn't have that. It means the relay CTs to provide triggering for the breaker to open during short circuit. These low voltage and some medium voltage breakers, the protection elements are integrated within the breaker itself. Okay. So you don't see CTs here and VTs because already the protection elements are within the breaker itself. But for the thermal element here, they use a CT, that thermal relay here, that model the thermal characteristic of this. So based on this current, they want to, if you exceed the thermal element, you want to open the contactors. So why we don't add also here an overcurrent relay, since we have a CT, and also open the contactor during short circuit? The problem here is the contactor is not designed to break high short circuit current. It will get damaged. So if you have a relay that sense a fault in the motor and try to give a command to a contactor to open, the contactor will get damaged. By manufacturer, most contactors by standard are designed to break up to 10 times its rated current. So if the rated current conductor of the conductor is, let's say, 100 ampere, they can break up to 1000 ampere safely without damage. If the current higher than 1000, it will get damaged. So you have 10 times its rated current capability. So if the short circuit current more than 10 times, and you have a relay that detect this short circuit and give a command to a breaker, the conductor, so it will get damaged. That's why we rely on a breaker now to trip this short circuit currents. But because overload normally is not higher than the starting currents, okay? And the starting current is not more than 10 times the rated current. That's why these contactors can uh, disconnect the motor during a starting current or during overload conditions. Um, Now, what are the motor information given to us? I want to set now the time and uh, time settings and pickup settings of this, the curve pickup settings for the thermal overload, and time and current settings for this. So what you are given here, the information given, this is 500 HP, the rated voltage is 2.4 kV, power factor 0.8, service factor 1, uh, the this is the motors by standard also classified into letters. Is so this is the letter G motors, uh, and uh, based on this letter normally they know which also what types of insulation, what type of insulation they have used for this insulation class. Thermal limit at with the low rotor is 5.5 seconds. So what does that mean? It is when the current at low rotor level, which is then uh, the you can wait up to 5.5 seconds before the insulation get damaged. This is like the safe stall time limit. The tip point I have mentioned here. This is this time point they provided. This time. So I have this time, I have also, that is direct start, there, because some motors can be started using star delta starter, using auto transformer starters, using soft start, which to reduce starting current, but this is direct, so you can apply rated voltage directly once you switch on the breaker. So we call it direct start. Uh, Duration of starting time is 1 second. What does that mean in the curve? It is this time, starting current. So the time once it starts will accelerate, then to reach the steady state this time. Okay, the starting current, the starting time. So the time for the motor to accelerate and reach the rated speed is 1 second. Uh, Thermal relay is specified. It has a coil rated 3.8. Here the rated current of the coil of the thermal relay. It has a tab from 90 to 100%, 110%. This is a standard range for thermal relays. You can change the settings from 90% to 110% of coil ratings of this rating in steps of 5. The CT ratio is given here, 150 to 5. We can determine it, no problem. If we measure, I will show you now, even if it is not given. The breakers, these breakers are, the setting values and characteristic curves are shown in the following figures. So these are the, I don't know if you can see it clearly, for the 200 breaker, this is the 200 breaker, you can set it at A, B, C, D, E as a pickup setting of 100 ampere to 125 at 150, 170 to up to 250 ampere for the 200 ampere relay breaker. 600 breaker, you can set it also at 300 up to 600 ampere. It has also a ground, this is for short circuit protection. It has also ground element. It's set at 15% of the rated current, 15% of the 200, for example, of the setting current here, 15% or 25%, 50%, 100%, okay, for ground fault protections. Uh, Now, where are these curves? Shows here the curves. Now, so the curve for the phase over current protection, it has different bands. So this is the first one band, okay. Uh, this is the band one, okay. So this band, I can set this. This is band one, band two, band three, okay. Uh, so this band means the relay. This is the called first of all. This is called this range uh, is called the long time curve. Uh, a relay has, sorry, breaker, low voltage breaker and medium voltage breakers can have this characteristic. The long time pickup current, which is the curves is something like this. This is band because they say at this current, let's say 2 times full load, the time, operating time between this value up to here. So this is a range. It's been tested. And if you apply 2 times, sometimes operate at this, sometimes operate at this time. So this is the range of operation. This is the band when you select band number 1. Okay. So this is called the time, the pickup setting for the long time curve. The pickup setting current is this, the middle point here. And as you can see, when the current is full load, higher than full load somewhere here, it's operating. So this is like a multiple of the full load of the setting. This is 100% means of the settings that you have selected. Let's say setting 100 ampere. So at 100% of 100 ampere, 2 times 200% of 100 ampere, and so forth. This is multiple. This is like plug setting multiplier. Okay, multiple of the settings. Uh, Now, so this is that long time setting. So do you have how many band? 1, 2, 3, 4, 5, 6 bands that you can choose to change the time. So this is like instead of time dial, I have time band to choose from to change the time setting. Now, in addition to this long time curve, it has short time curve, which is shown in 3 also settings. We have 1, medium, maximum, and intermediate, and uh, and minimum. Okay, so if I can choose, let's say, this is called the short time delay for the short time delay curves. These are the for 1, 2, 3 are for short time. So if I can set it at a medium setting, so the curve will looks like. So this is in the medium band. So if I choose my short time pickup setting at this level. Now if I choose the short time pickup setting at this level, the curve will looks like for the short time elements, uh, like this one, for example. So this is, I change the pickup setting up to here for the short time curves. So short times, I can change this to up to here. from here. This is like time pickup setting for the shift time curves. I can shift this curve uh, from minimum here up to maximum here. And the time delay of this short time delay, I can set it from here up to minimum is here. This one, the lowest one is here. So this is I can change the time by choosing minimum band or intermediate band or the maximum band. This is for the short time delay. It has also instantaneous the elements, which is this one, the instantaneous, this one. So the instantaneous, I will draw it here, is another band. This is the instantaneous element. I can change also the instantaneous elements from this pickup value, but I cannot change the time because this is instantaneous. I can change it from here up to a level for the instantaneous. So where this setting is here, this is the breaker. This is the handle to switch on off, and these are the settings area. So this is the one that I am showing you now. These are the settings which is shown here. Uh, so this is for the long time setting band. This is the time setting. First of all, long time pickup setting. So I'm setting this value, the pickup setting of this long time curve, the red one. I'm setting also the time, which of these bands I want to choose. Okay, and so the time band is this is the long time pickup, and this is the long time band, which is the time. I can choose it 1, 2, 3, 4, 5, 6 bands. I have 6 bands. 1, 2, 3, 4, 5, 6 bands for the timing. For the short time pickup, this is the short time pickup. I can add 3x, 5x, 8x, and 12x. 12, 5x, which means times the pickup setting that you have chosen. Pickup setting of the long time pickup is A, B, C, D, E, G, which is these. A, B, C, D. For 200 ampere, I put it at E, at D, for example. This means you set it at 175%. Sorry, 175 ampere pickup setting. So the for short time pickup setting, you can this is the pickup setting for current pickup setting. For time setting for the short time, this is the short time band setting, which is you are changing this, the green one here, either minimum, intermediate, or maximum band for the short time curves. And for the instantaneous, this is for the instantaneous pickup setting at 3x, 5x, 8x, and 12x. Okay, you can set it. And for the ground is shown here at at this is air fault current in percent of the trip value rating. يعني in terms of the one trip settings here. So at 10% or 20%, 30%, 50%, 70%, 100% of the for the current. Now we have for the ground we have you can have the pickup setting and the time also settings. You have minimum time, intermediate time, and maximum time setting for the earth, and for the pickup you can change it from here up to here, the pickup setting, because you have 15%, 25%, 50%, and 100%. Four pickup settings you can choose from. For the ground, I have the pickup setting for the ground. We have 15%, 20%, 50%, 100% of those pickup setting for the, and the time setting is here. Three bands: minimum, intermediate, and rate. So this is the breaker itself. Okay. Now, how do you choose this timing? And now the overload is this has also an overload targets, but now the overload is provided by the motor. Okay. So by the thermal relay, which is here. So let's set this one. Do you have any questions, Shabab? With regards to this, looks like complicated, but basically the curve, something like this one. The curve is for this types of relays. This is the time versus current. And now this is normally, this value is your pickup setting for the short time. Okay, so this is the short time. So this is the short time element. Sorry, long time element. This is the long time, they call it. Long time. So it's like a 51 element, okay, isn't it? So this is equivalent to a 51 time over current relay, where the pickup is here. This is I pickup. Normally, if it's a multiple, this is one. Your pickup setting for the time. One as a multiple, so your pickup is here. And the time setting, this curve can be make it down or up, depends on which band you choose. Okay, so it has also a time setting instead of a time dial. Here a time band, which band you choose. This is only one curve now. The difference here is just to tolerance that this relay, this breaker can take a range of. This is a tolerance that the relay will, the breaker will operate within this range. And the second one is the long time, this part. This is the short time. This is the short time element. And the short time elements also has a time setting and a pickup setting. Its pickup setting is this one, where it's operate. Okay, and its time setting is this, which is this level, which is here. I say have three bands for the time setting: medium, low, and high. But now, not the third is the instantaneous. This is the instantaneous. So this is equivalent to what? This is like equivalent to a definite time over current relay, or instantaneous with definite time. You can change the time. This is the instantaneous level, and this is definite time. So this is like also 50 element, but with time delay, with definite time delay. Time delay. Now this is the instantaneous. There is no time delay here. So this is all equivalent to a 50 element. So the pickup setting of this is here. This is its pickup my I instantaneous. But here I instantaneous is given as a multiple of this. Okay, at 5 times from this breaker uh, at where is the instantaneous here? At 3 times, 5 times, 8 times, 12 times the that setting of this setting, okay, of the long time settings. So these are basically, now I can have different curves for the long times, different curve for the short time. This can be set here for the pickup. I can set also for the pickup for this. I can change this curve right and left. I can change the curve this up and down based on time setting for the long time. This also can be shifted up and down based on the time setting for the short time elements. For the instantaneous, I cannot change time. I can change only the pickup setting. So these are the variation. Combining these three elements in the breaker will provide flexibility to protect, to provide coordination and provide best protections for sensitivity and selectivity. Now, if I go to the solution now, what will we start? I will start with thermal overload. I will start with this one. This required the full load current to know. To get the setting, as I mentioned, my settings for overload, I have to set it, what is the 40? I have to set it normally 5% higher than the, yeah, here. Well, I have to set it at this way, 5% higher than the safety factor times the full load current. So I have to find the full load current first. So full load current of the motor 5 HP times 746 watt per HP times over root 3 times 2.4 kV, kV, or you can put here in volt and this is in watt, so you can cancel the 0.8 factor. This is the rated current. Now that's why it's, you know, they choose the CT of 150 to 5. Now, how do you choose the CT normally? I should also multiply by safety factor, and you choose a current for a CT, current rated current higher than that value. So this is the rated current. This is called the full load amp or full load current, nominal currents. Now, what's the lock? I need another information is important that I know the lock rotor current. The current from here they give me the lock rotor time, but he didn't give me the lock rotor current. From the standard, if you go to class G motors, they give you this is the starting current correspond to class G motors. So I went to the standards. This is standard for the code letter for the motor and the maximum, the range of kilovolt ampere per horsepower with at locked rocker current. So for class G, he says that the lock rotor kilovolt ampere per 1 horsepower from 5.6 to 6.29. So I took the worst value, the highest value, to get the highest lock rotor current. So from this 6.25, 6.29, not 25, 29, 6.29 kVA per HP. This is in kVA per HP times 500 HP. This gives you kVA. divide power root 3 over 2.4 give you the current. This is the locked rotor current, locked rotor current. Also, you can abbreviate it like this. I lock rotor. Now this is the, and some motor, they will give you this information directly on the nameplate, so you don't have to calculate it in this way. So I got the lock rotor current. So what does mean? If the current is this, the motor will take 5.4 seconds to accelerate and reach, sorry, this is the maximum time you should wait before a motor will get damaged. Okay, so this is, and so I want the protection to act before 5.5 seconds. All right. While this is the acceleration, the motor takes 1 second to accelerate to the rated speed. So this is very important because I want to act at this current, I want to act before 5.5 seconds. Okay. So how do we now set the thermal overload relay? The pickup settings for the 49 element. This is the 49 element. 1.05 times safety factor times full load current. This gives me this one current. And so in this relay, thermal relay, you have a settings from 90% to 100% in steps of 5% of this value. So I have to find the current here correspond to the full load current. And then I see this current as a percentage of the 3.89, the current coil, rated current of the current coil of this relay. So this is an older technology, okay? So what is the corresponding current at the secondary side? I multiply by 5 over 150, I get 3.93 here. So 3.93 here. Now, with respect to this rated current coil of the thermal overload relay, this represents the percentages. If you divide it by 3.83, okay, which is the rated current of the overload coil, relay coil, that gives times 100 give me, this is 101%.5. Okay, so that means I can put it at a tab of 100%. I can put it at 100%, not 90, not 95, 100%. Tab. So now at 100% tab, the pickup value for the thermal overload is 3.8 times 100%. 100% times 3.8 is current, rated current of the thermal relay times 150 give me the current at the second primary side. So means when the current reach 116, the thermal relay will start to operate. So start not to trip, so it will take time based on the curve that you will choose now. So how do you choose the curve? The curve, you will choose the curve now that match. Now at the starting current, you should choose a curve that provide a minimum. I didn't give you here the thermal relay. I'll give you the curve for the thermal overcurrent relay. Also, you have to check that the lowest point of the curve at the starting current should be below the thermal limit, 5.5 seconds at locked rotor current. Now setting the breaker, which is at the top, this one. So what does this show? This will give me thermal overload at moderate overload conditions, but I want to provide another protection here. We provide for short circuit for when the rotor is locked. I can trip with this one and so forth. and short circuit also protection. So the range of values that I can choose for the long time element, I showed you long time elements, the pickup setting from this up to here. From 100 ampere, this is I showed you 100 ampere for the 200 ampere, 125, 150, 175, up to 250. So these are the available pickup setting for the long time element. So which one of these I should choose? So the normally the pickup settings, I can choose it also at 1.105 times safety factor times this, but I can also choose it at up to what's the maximum value for these. Normally you should not exceed 115% when the safety factor is 1. This is the maximum for safety factor 1, and 125%, this is maximum setting when safety factor equal to 1.15. This is the limit. So, but you shouldn't go below 1.05. Okay. So this is basically is also provide a thermal overload. So 1 to 1.05 times the safety factor times the full load current. This gives me the current pickup. The minimum current pickup should not go below this. So from that, the nearest one is not 100, it's 125 is our setting. So this provide like 111%, so within the maximum limits. So this is the maximum setting, which is within 115%. So I want now, what's the time? So which of these band I have to do? 1 to 6, which one of these? So those one has to be coordinated at the starting current. So when I have, so I have to choose my starting current is here. I have to choose this point on the curve, which is higher than the starting current. So higher than the starting current. So how do I or below? So this is higher than the starting current time, which is 1 second, and below the 5.5 seconds. So first of all, so I got the pickup settings, and now at time I should look now the current of the starting current. So this is my value at which I want to set the time. Okay, and you know that the lock rotor at this current and the starting current of the motor is 1 second. So I don't want this element, the short time element, to operate while the motor is starting. So I should delay this minimum of 1 second, higher than 1 second by a margin. So if you go to the curves here at 756, represent how many times of this like black setting multiplier. So the starting current by the pickup setting give me 6 times. So I go to the 6 times, which is here. Okay, and I go up and see what is the time for the lowest band. Sorry, and the time I set the time I want 1.4. Why? Because the starting accelerating time is 1 second. I added 0.4 seconds as a safety margin so that the relay this breaker will not trip during starting. So I need a minimum of 1.4 second. This is 1.4 second desired, and they intersect here. In the first band, lower band. So if I choose this band, means there is a possibility, like, because this band starts from here up to here for time. So there is a possibility that I will not achieve this margin. Okay, so for that's why I'll choose the next upper band, because the intersection lies in the band, is not below the band. So I go to the next band. So the next band is band 2. I will not choose band 1, I'll choose band 2 for my time setting. So this is the first criteria for choosing the timing of the long time delay. All right, so that's practically, it will give me a minimum at this time, minimum of roughly 2 seconds operating time. Now I've finished from the long time element. I want to choose the short time element, pickup and time. So the pickup also now the short time normally is used to detect also locked rotor condition. So I have to set the time, the pickup setting greater than the uh, locked rotor current by a margin, and it has to be time delay. So uh, when you look to the curve here, so I want to choose this setting higher than the lock rotor current. This is because this is an instantaneous element. So this provides short circuit. For short circuit protection, as I mentioned here, we want to choose it. So this long time, this is like the short time. This is representing something like the short time element, and this is the instantaneous elements. So I want to choose this. So how do I choose this? Short time elements. I want to take 1.2 to 1.5 lock rotor current and delay it by a time. Uh, this is the so this has to be greater than lock rotor current by a margin. So I choose from 1.2 to 1. I choose 1.3. So 1.3 times the starting current, this is the starting current, okay? And that represents 7.9 times the rated current. Because all the settings here with respect to the pickup uh, of the long time element. So in percentage of this current, which is 1.3 times, look, represent almost 8 times pickup settings of the long time. So I'll set it at 8 times. So in here, I'll choose at 8 times for short time pickup at 8 times. And for 125, so 125 ampere represent here, represent B. So I'll set the element at B here for long time pickup setter. So I choose this. Now I choose also the pickup. So everything now is taken with respect to this in terms of this times with respect to B, which is 125 ampere. So I choose now at 8 times the pickup settings, which is equivalent to 1000 ampere at the uh, primary current. Now, how do you choose the setting now for the time settings? Uh, now, normally we set this one to have 10 cycle delay, 10 cycle delays, 10 cycle over 20 millisecond, over one cycle is 20 milliseconds. So this is roughly 0.2 seconds delay. So I want to choose now at this starting current, at this value, which is at 8, the pickup, 8 times the pickup. So where is 8 time pickup? Okay. Uh, so this is the 8 times. 7, 8 times. So at the 8th time, I want to provide 0.2 seconds as a coordination. Okay. So the lowest one, okay, the lowest one, uh, the minimum band, so the minimum band here gives me a 0.1 second. So this is the, you can see, this is the minimum time, which will start from here, okay, up to here. This is the range for the minimum. So it's possibly that it will operate even at point this time, up to this range. So I won't choose the minimum because it won't satisfy 0.2 seconds time delay. So I'll go to the second one. See, the 0.2 seconds, it's achieved at in the intermediate band, which is here. The intermediate start from this time up to this time. So that's why I chose the intermediate band to give me a 0.2 second time delay at 8 times the pickup settings. So I achieved this will overcome the asymmetrical current of the starting current, this time delay. Because I am very close to the lock rotor currents. But if I choose 1.7 times lock rotor, I don't need to have weight because this is sure 1.7 times lock rotor. This is for sure a short circuit. It's not the asymmetrical current of the starting current. This is what we'll do for the instantaneous later. So I finished from the for the instantaneous elements. It has also I don't have 11, sorry. Yeah, I have 11, 8, 3, 5, 8, 11, and 12. And now I'll choose this as 1.7 times lock rotor, and this indicates the presence of a short circuit for sure. And I have want to wait. So this is the current correspond to 1.7 times the starting current. And that represents, if I divide it by 125, it gives me 10.3 per times. So 10.3 times I'll choose as a settings 11 times. Okay. So I'll choose now 11 times 125 as your pickup setting for the instantaneous element. I'm finished from breaker, from this breaker. Now, how do I choose this breaker timing? Assuming I have also motors fed from the same bus bar. So your full load current here is not same as the motor current because you don't know the other feeders leaving this bus. So I have to take the full load current from the transformer rating. So my full load current is this current of the full load of the transformer LV side full load current to set this one. So we'll do the same thing, but using now the breaker 600 breaker. Our full load current is the transformer rating over the, I get this is the full load current. And now, based on this, this is very close, okay? Doesn't give me, so I'll pick now the 400 ampere, and 400 ampere give me, this won't give me a 5% margin, okay? So this will give me at least between 5% to, for safety factor 1, I can put the from 5% to 15% extra than full load as a pickup settings. So 400 ampere selected. If you divide it by the full load current, that represent 110.8%, 111%, so which is higher than 105% and less than 115%. It's okay. Selection of time band. So in the same way, so I have to coordinate now. I have to coordinate. This is the for the 200 breaker, the long time element, the short time elements, and the instantaneous element. Okay, for the breaker. This is the pickup settings for the. Now, to coordinate between the 600 breaker, I have to coordinate at this point. So at this point, at which the short time elements, which represent the instantaneous element, operate at this time, I have to add a coordination time interval. Okay, and I choose this. Then I choose the curve for the long time of this. This pickup setting of the breaker 600 pickup time already based on full load current. We chose it already. We chose already this, but I want to set which band for the long time. So I have to choose at this current first. What is the time at this current? This current already we know it's operate at 1000 or the at 1000 from here for the short time element at 1000 set at 8 times 1000. So at 1000 I want to see what was the operating time of the 200 breaker. So from the curve at 1000 over 125 to represent 8 times. At 8 times from the curve, at 8 times from the curve, it gives me the operating time of not this one. I have to go for the long time at 8 times. Okay, it gives me this one for band 2 because the band 2 is my setting, so it gives me at 8 times a minimum is minimum here as can band 2 intermediate band. So no, this one was band 2. Yes, band 2 at 8 times. 8 times, you see it's the current will be about 1.5 seconds. So this is the 1.5 seconds from the curve at band 2 at this 8 times. And for now, transformer breaker, which is the 600 ampere breaker, I have to add a coordination time 1.5 plus the coordination time 0.2 seconds between the breakers, low voltage breaker. This is I covered in the overcurrent protection, and I give it 1.7 seconds. So if you go to 1000 over the 400 pickup settings of this transformer breaker, so that we choose is 400. So 1000 ampere, same that at which I calculated the 200 breaker time. I have to use the same current for coordination. So this represents 2.5 times, and to get 1.7 seconds, okay, sorry, to get 2.5 seconds, so 1.7 seconds at 2.5 times, a C point band 1 is sufficient. At 2.5 times is here, okay, and the at 2.5 times the band 1 already will give me something 6 seconds roughly, more than 1.7 that I wanted. So I'll go to band 1. So in this case, for the long time is band 1 is chosen. For the now, what is the short time? Short time elements, the pickups I choose at 6 times the full load, or at the start also starting current. I don't want to have the relay at the breaker 200. I don't want to start this. I don't want to this operate when the motor is starting. So I have to coordinate also with the short time of this has to coordinate with short time of this. Okay, the short time of this I know it was set as a short time of this has to, short time of the 200 breaker was set in the intermediate, okay, band. So I have also to make sure there is a coordination time between the short band this and the short band of the 200 breaker. So um, uh, at this current, this is 6 times the full load ampere over 100. This will be 5 times, and at this current, uh, the the breaker band, I'll choose the also intermediate time. So in the intermediate, if you go to the intermediate at 6 times, okay, it gives me the intermediate because why also if you, even if you can use the starting current, even if you use the starting current, the because the this is the pickup settings 400 and this is 125 ampere set at 125 ampere, and this is 6 at 400 ampere pickup. The starting current with respect to this may be 8 times, but with respect to 400 will be less. That's why this will take longer time as compared to this. So with the same, we'll choose the time for the short time element. For instantaneous will be disabled because there is no, I cannot choose now the instantaneous for this. If I choose instantaneous for this at this level, for example, what will happen if a fault happens here, short circuit level here, then this operate and this operate at the same time. So I will disable the instantaneous element at the 600 breaker. Unless, because here we have, why do we do this? Because now a fault here at the terminal of the motor and a fault here is same and a fault here is same. So that's why you cannot have instantaneous. You put an instantaneous here, you cannot put it here because when you have margin, as I mentioned in the coordination, you have margin between a current seen by this short circuit current and this short circuit current. So that's why I will disable the elements instantaneous at 600 ampere. And this is the characteristics when you draw them. This is for the 600 breaker, this is for the 200 breaker, and this is for the thermal overload element, the 49 elements. And I didn't choose now the ground. So the ground over current relay is set at, let's say, 40% of the full load settings. Now for this is at, let's say, 125 ampere pickup setting. I can choose it at 40% of this, and I can delay it by, as the recommendations given here in the notes for the ground over current relay. Normally we delay it by 0.2 seconds as mentioned here. If you choose normally we choose at 40% to 60% of the full load current. For the 200 breaker, it's 125 ampere was its setting. It's 40% of 25%. You choose it okay, and you choose it delayed by 0.2 seconds. You choose the curve that gives you a delay. Now you choose this curve band that gives you a delay of 0.2 seconds. So this is the 0.2 seconds. All right. So here I will choose the intermediate band for the ground, but for the pickup now for 40, if I take 40% of my full load amp, or you can even take it 40% of the pickup setting. So if you take 40%, so here 25% and here 50, so I'll choose here 50% directly. So my ground over current protection is 50% of your pickups, long time pickup setting. and delayed by intermediate band, because that will give me 0.2 second time delay correlation. And that's it. I'm done for the ground fault protections uh, for this. Now for the breaker, main breaker, if you want also to set the ground over current, so if we have a ground, if this failed to trip this and you want this to operate, then you also have to coordinate between the ground here over current relay on the ground here. So this has to be delayed. So in term here, you should, for the ground over current relay for 600 breaker, you should hit at maximum in this case, because that you choose at minimum, which will provide 0.2, so that they will not overlap. And that's it, Shabab. I talk more than the lecture time. Sorry for this. With this, I would like to conclude this chapter.